Can you hear us?
I can hear you. Can you hear me?
Yes, we can hear you just fine.
All right.
And in just a second, I'll turn this thing around so you can see the class. But you're going to want your what's that?
The camera on your thing.
What's that?
I'm gonna make sure.
Oh, right now we don't have the distance learning thing going, do we?
What do you mean share screen?
Oh,
Yeah. I mean, you can point at the screen there, so they can.
yeah, it's on the track. I just got through.
Oh, okay, great. All right. Let me get his slides.
And I'm just going to share my screen, so
Okay, so I don't need those. Okay, you're going to show your screen. All right, great. Kevin did this to a similar presentation to my other class, and I had it pointing at the blackboard the entire time, so all I could see was the blackboard. So, so this should be a little better. So that's Kevin McLaughlin, and he was a student here. Kevin was a LEAP student. He then got his master's in engineering, and is now working in Austin, Texas. For how long have you been there, Kevin?
about 2 years.
About 2 years. So he also did some research with me on, you remember I showed you this simulation of the electron going around, right, and ionizing it. So he did some work on that with me. He's very good at programming. And he read this, or something stimulated his interest in this particular problem, and he put together this simulation study of taxis in the Uber company, and which he's going to talk about, and sent me a note and said, "Hey Dan, what do you think?" I go, "Wow, that's really cool. I think you ought to show this in my class." So that's where we're at. So Kevin, why don't I turn it over to you?
Great.
All right, cool. Can you see people okay, or?
Can you just tilt the camera down a little bit? I think it would be a little better.
Is that good?
Perfect. Great.
All right, great.
Cool. And everyone can see my screen?
Yeah.
Okay, cool. Okay, so yeah, I'm Kevin McLaughlin. I created this Uber surge pricing simulation because I was sort of interested in how important surge pricing was to Uber. I had a few discussions with some people that thought that surge pricing, well, they had widely variant opinions on whether surge pricing was fair or effective or anything. And so I created this demonstration and wrote an article about it to sort of demonstrate how important surge pricing is to Uber. So without further ado, I'll get started here. All right. Everyone can see the presentation here?
Yeah, it looks good.
All right, good. Okay. So this is the Uber surge pricing simulation. The simulation is publicly available on countingcalculi.com. It's at Interactive's Uber v Taxis. It's pretty easy to find when you get there. So if you're interested, you can go to the site and sort of play with the simulation yourself. And all the code is open source and on GitHub as well. So, okay, so a little introduction. Uber, in case you haven't heard, Uber operates the Uber smartphone app that allows passengers to request rides from Uber drivers directly through the app. Something that's different about Uber from taxis outside of the smartphone app is that anyone with a car can sign up to become an Uber driver, right? So just so long as you have a car, I think the limit is it has to be 2008 or older, you can go to Uber and you can sign up to be an Uber driver, and you can start picking people up through the app. Another really important piece of Uber is that Uber uses surge pricing, which is what we're talking about here, to raise prices during periods of high demand to encourage more drivers to get on the road. So since Uber relies on independent contractor drivers, since anyone can sign up to become an Uber driver and you can hit the road anytime you want, Uber has to incentivize its drivers to get out onto the road to pick up people. So they came up with this surge pricing algorithm, right? And surge prices raises or lowers the price of a ride based on the supply of drivers who are out on the road and the demand for rides, right? So basic supply and demand is when the quantity of drivers goes up relative to the demand, the price will drop along this curve. The supply curve will move to the right, and the price point here, the equilibrium point, will go down, so it'll be cheaper. Similarly, the other way, if the demand goes up relative to the supply, the price point rises up the demand curve and the price goes up. So you can imagine that 2 a.m. on a Saturday night, there's a lot more demand for rides than there is at 2 a.m. on a Wednesday night, right? So Uber created this surge pricing. They actually piloted it in Boston. It was the first place they tried it out to just try to get more drivers on the road during periods of high demand. And it turned out to work just incredibly well, at least so they thought. And so that's what we're investigating here today. So the simulation, the goal of the simulation is to test how Uber's surge pricing model compares to a more traditional fixed price model of taxis. So taxis prices are actually usually set by the city that they're in. So Boston City Council sets the rate that taxi drivers can charge. Uber's is not fixed like that. Like, the surge pricing, just the price can go up and down depending on supply and demand, right? Something that's interesting about this simulation and Uber in general is that they're using technology and basic principles of economics in this simulation to study a real life business model. So I think that's why Dan found this particularly interesting. So, Uber probably has a simulation that's similar to this to test their surge pricing algorithm against. Obviously ours is probably not as sophisticated, but it can still help us examine a real working business model that's out there. Right? So we're going to run an experiment. That's really what a simulation is. We're going to run an experiment, and we want to find out how important surge pricing is to Uber, right? So our hypothesis is that the surge pricing is critical to Uber's success based on 3 factors, right? How long a passenger has to wait for a ride, right? That's obviously important. How much the ride costs and how much the drivers make. So Uber has to balance all 3 of these interests, right? And you'll see in the simulation, all 3 of them are tracked in the simulation. So the way that we're going to test our hypothesis is we're going to compare Uber's surge pricing to taxi's fixed pricing without any other advantages, right? So in the real world, Uber has a very nice smartphone app that you can request a ride through, and actually it allocates drivers to passengers. So you don't have to, on a taxi, you basically have to end up in the same spot as a taxi randomly to get a taxi. Uber will allocate rides, will allocate drivers to passengers. But in our experiment, since we're just trying to find out how important the surge pricing is in particular, we're going to eliminate those other variables. So the Uber world in this simulation, has no other advantage except for their surge pricing and their flexible supply of drivers. So we have this hypothesis, we have this great experiment that really isolates the variable we're interested in, but Uber isn't just going to let us run this. They're not just going to shut down their other advantages for a night to let us, experiment and test our hypothesis. So what we need is a model. We need a way to test our hypothesis that's not just an experiment in the real world, because that's impractical. So a couple of model tools we'll be using. It's a basic time stepping model. I think you all have talked about time stepping. It'll rely heavily on randomness, right? Which is often called a Monte Carlo simulation. And we'll talk about these all in detail as we go along. And it's also going to use a normal curve to model human behavior. So there's a lot of human decisions that go into Uber's business model. We're going to model them with a normal curve. So we'll talk about that in detail when we get there. I have a couple of general notes on models. First, and probably most importantly, a model is not just a replica of reality. We're not trying to recreate reality in a digital form, right? That's not what a good model would do, right? The essence of a model is to simplify the real world and to break it down into bite-sized chunks so we can find out something about the world. So we want to filter out a lot of the things that we're gonna assume are not important to really isolate and try to figure out what we're interested in. All models rely on simplifying assumptions to approximate and highlight the most important features. So I think everybody in this class, this being an engineering class, has taken Physics 101, right? And the first thing that they do in Physics 101 is they tell you to solve a problem without air resistance. How fast does a rock fall without air resistance? Or imagine a world in a frictionless, in a frictionless plane or something like that, right? Like the comic over here, right? That's a model, right? The real world does have air resistance. The real world does have friction, right? But you make a simplifying assumption because what you're interested in is studying the effects of gravity, or you're interested in studying momentum, right? And making your model more and more complicated to just for the purpose of eliminating assumptions is not always the best way to get at what you're interested in. So really, really important part of models is that you have clearly stated simplifying assumptions. Another important thing about models is that they're fundamentally pragmatic, right? We want to achieve some goal with a model. We don't want to try to recreate reality with all its nuances and intricacies. We want to look at one particular thing, and we're going to design our model to examine or achieve some goal, right? So as a result, a simple, easily implemented model is usually more useful than a complex, convoluted one, right? The simulation we're going to look at here, I created, on my free time. I have a day job. It just would have been totally impossible for me to try to account for, a lot of things that weren't really relevant to what I was studying, right? So in that way, a simple, easily implemented model is a really, really, important part of modeling. And often the goal of the model is just the beginning of the investigation. So follow-up investigations might require a more refined or an altogether different model to investigate or achieve a different goal, right? So the example I like to give is you might have one model if you're trying to study what is the average rate of return on the S&P 500, right? That would be one model. If you were trying to study predict when the next recession was going to be, you would need a very, very different model than what the average return on investment is going to be, right? Those are just two completely different goals, and it would be very, very difficult, if not impossible, to create one model to account for both of them, right? So, quick overview here of the simulation. The purpose of the simulation is to test how important surge pricing is to Uber by comparing an Uber world to a taxi world. So what the simulation looks like, I'll show you what the simulation looks like so that way you have an idea while we're going along. There's an Uber world and a taxi world, right? And you'll see cars driving around just like this, right? And the results will be graphed here. And you'll see a couple of variables that we're interested in studying are updated down here. And then there's also some settings that we can update if we want to test different scenarios. So this is what the simulation looks like overall. Okay. And there's some important things about this simulation. First, it's built in JavaScript and jQuery if you're interested in. It's totally in JavaScript. And it divides the city into a simple grid. So you can see this is a pretty simple grid here. It uses linear time stepping for each movement of the cars. So it's not, you know, fourth order runge kata or anything. It's just simple, basic time stepping, sort of like Euler's method, right? Cars move and passengers appear randomly in the city. So you can see the cars driving around. Those are the cars. The passengers are the little dots. They just appear randomly. The number of Uber drivers is determined by the demand for riders, while the number of taxis is fixed. So this is actually a taxi world here, and the total number of taxis is fixed. So the only difference between the Uber world and the taxi world is that the Uber world has a flexible supply of drivers that respond to a surge incentive. So increasing prices causes more drivers to get on the road. That increasing price is determined by the supply of drivers currently on the road and the demand for ride requests. So again, just to show you the simulation, right? Here's the Uber world, here's the taxi world. You can see if you watch for even just a little bit, the number of Uber drivers change while the number of taxi drivers doesn't. Okay. So, like I said, every model has simplifying assumptions, and ours has absolutely a bunch of simplifying assumptions. There's a lot of them, but the four most important things are that we're assuming a city can be approximated as this simple symmetrical grid you see down here. We're also assuming that the movement of cars and passage of time can be approximated in a simple linear time step, right? So if you watch carefully here, you notice all the movement happens simultaneously. All the cars move at the same time, at the same speed. That's because they're all just moving one step every time step. And the time steps are linear. It's not, like I said, runge kata or anything like that. Drivers move and passengers appear randomly. That's the Monte Carlo part that we were talking about. They just appear randomly in this city. They don't, you know, in the real world, they would probably appear in clusters somehow, right? You know, a concert would let out and a bunch of passengers would appear in the same spot. But we're not going to account for that level of sophistication in this simulation. And then the big important thing is we're going to assume that Uber drivers respond to financial incentives, but taxi drivers do not, right? So that may be an assumption you could challenge in the real world, but we can talk about that when we compare some results to some real world data, and we'll see whether or not that was a good assumption. Okay. So we have this grid. It's a pretty simple grid, right? You can see this looks like this is a Manhattan city block. It's not a Boston city block. So, you know, things are nice and orderly, right? This is actually a grid, just like you would see on graph paper, right? The city's divided into grids, right? Each grid is assigned, each little square is assigned a number. So they're indexed like you would expect. There's an x-axis and a y-axis that goes down. The first one's 0, 0. This is 1, 0, right? And this extends all the way through the grid, right? So each car is assigned, when they're in a position, they're assigned to a box, basically, or one of these squares, right? These squares here that are colored differently, those are obstacles, right? So those are like buildings, and no passengers or cars can go into those indexes there, or those squares, right? The time stepping, a car moves one cell each time step, one cell, one square each time step, right? So if a car was here at 0, 0 and it was going this way, in one time step, it would move like that, one time step over, right? When a car comes to a turn, it makes a decision based on, it's just totally random, right? So it comes to an intersection like this, and it has an option to turn right, go straight, or turn left, right? So basically it's like the driver rolls a dice. He has a 3-sided die, he rolls the dice, and it tells him right, left, or straight. That's often the way that they describe Monte Carlo simulations, is just like you're rolling a dice. That's where the term comes from, because it's like you're gambling in Monte Carlo. I guess they could call it a Las Vegas simulation too. But I think it was before Las Vegas was, well, made. So, all right. So passengers and pickups. Passengers will just appear randomly in a randomly selected cell. So you remember each of these squares is a cell. So a passenger is just going to pop up randomly like that, right? When drivers and passengers end up in the same cell, the driver can pick up the passenger, right? So it's sort of like taxis, where you have to end up in the same spot as the taxi to be able to get a ride, right? Like we talked about, Uber's not allocating rides or anything. So you'll see here the car and the passenger, when they end up in the same cell, the car will turn green and the passenger gets picked up, just like that, right? And they're on their way. If the car already has a passenger, it obviously can't pick up a new passenger, even if it is in the same spot. We're going to have a number of inputs. These inputs are adjustable, like you can see here, right? So the number of taxis is fixed. So once the simulation starts, the number of taxis won't change. But before the simulation, to run it in different scenarios, you can change the number of taxis. You can make it, I think the default is 10, but you can make it 5 or 50 to test different scenarios. You can also change the other, basically, prices here. Right, those are adjustable. Now, the Uber drivers don't just have there's not just a number of Uber drivers. So the Uber drivers are determined based on the surge pricing, right? They're incentivized by the surge pricing. And the way that they're incentivized by the surge pricing is this Uber driver incentive curve, right? So if we look back at the simulation, it's this curve down here, right? This guy here, I'll zoom in. Right, so this Uber driver incentive curve is a normal distribution. It's a cumulative distribution function. So it's just a normal curve. It's a bell curve if it was in the, you're probably more used to seeing it in the PDF format instead of the CDF format, right? Then it looks like a bell curve. But in the cumulative distribution format, it looks like this, right? And what this is telling us right now is this cumulative distribution function has a mean of 1.5. So if the surge is 1.5, right? So at a surge price of 1.5 or 1.5 times the baseline surge price, right? So in this simulation here, it would be 15 cents per minute, right? That means that 50 Uber drivers will be on the road. A total of 50 Uber drivers will be on the road. At the baseline price, at 1 times the baseline price, there'll be 5 Uber drivers on the road, right? When we get up to 2.3, a 2.3 times surge about here, all 100 Uber drivers will be on the road. So this is the example of the normal curve modeling human behavior. So the assumption here could be phrased a different way, is that let's suppose there's 100 Uber drivers for this little city that we're imagining here, right? There's 100 Uber drivers, and you know, about 5% of them are going to drive for just the baseline price. To get 50% of them to drive, though, you know, maybe their time's a little bit more valuable. Maybe they make a little more money at their day job. Maybe they have a kid, so it's not their time is more valuable, right? For them, it's going to take a surge price of 1.5 for them to get on the road, right? And then there's another group over here, you know, maybe they're investment bankers, right? So it takes a whole 2.3 surge for them to be incentivized enough to drive, right? That's another way to think about how this is modeling human behavior. What's nice about this incentive curve is it's adjustable. You can adjust the mean here and see how it affects the curve, right? So we can go all the way over here where this is basically saying that, you know, it's going to take a surge price of 5x even to just get about 40 people on the road, or I can go all the way to the bottom. This means just everybody's going to drive for the 1x surge. So the mean's adjustable up here, and the standard deviation is adjustable over here. Any questions about those inputs? Okay, I'll keep going. So we're going to test with the default test case, right? So there's a default when you first come to the site. We're just going to stick with the default inputs. That's 10 taxis, a price per minute for taxis of 25 cents per minute, and an Uber surge price, a baseline surge price of 10 cents per minute, right? So that's down here. That's at the one-time surge. We're going to leave the Uber incentive curve as is, and we're also going to let it auto change the demand. So you can update the demand manually here with this slider. You can see I go up and a lot more dots come on, and I drop it, and the number of requests plummets after I drop it. We're just going to leave it with this auto change demand function to just study the default case. All right, so we'll get started here. I'll zoom in a little bit. So you can see here the drivers are driving around, right? Right now there's not too much difference between the Uber world and the taxi world. They're just sort of, it's pretty low demand here, right? Like it would be at, you know, 1:30 in the afternoon on a typical day, right? And you can see here on the graph, we're updating the results in real time. The graph is being drawn in real time here. The light blue is the number of Uber drivers that are currently on the road. The red is the surge price. Here's the surge price axis, right? So that's the 1x, 2x surge price. The purple is the number of taxi requests currently out there. So that's the purple dots, right? And the deep blue is the number of Uber requests out there, right? So we can see already demand's starting to creep up, right? We have this inconsistent demand, and you can see right here, demand shot up a little bit, so the surge price went up and the number of Uber drivers went up just like we would expect. Since the number of taxi drivers are fixed though, taxis have a hard time keeping up with spikes in demand like that, right? So we can see right here, the number of taxi requests didn't even get back to 0 before the next spike. And now we're spiking. This is like really, really heavy demand, right? This is like a concert just let out downtown or something, right? And you see the taxis are just completely overwhelmed. But because the Uber drivers can respond to incentives, right, they can get more drivers on the road. And you can see that they've already filled all the requests out there for Uber drivers. You can see that here over on the graph, the surge price shot up. The number of Uber drivers actually maxed out. And right about here at 6:30, when demand ended, right, when this spike stopped, the concert, you know, stopped or whatever, right, Uber just basically gave everybody who wanted a ride within an hour, they got a ride. Taxis, meanwhile, are still trying to get everybody, right? We're looking at, it's getting close to 11:30 here, about 4 hours after the concert ended, and actually at midnight when the simulation ends, taxis still haven't picked up everybody, right? So we can see right here, just from a rough analysis of this graph, that Uber, especially in changes in periods of high demand, is just much more effective at allocating rides, right? At getting people rides quickly. You can see how quickly Uber right here took care of everybody who wanted a ride, while the taxis couldn't even do it, more than 4 hours later, right? So we also tracked a couple of statistics here. Remember, we're interested in 3 big things: how long it takes to get a ride, how expensive that ride is, and how much the drivers are going to make, right? Because the drivers are going to stop driving for Uber if they don't make enough money, right? So we'll look closely at the results here, right? So for this simulation, the average wait time for Uber was 17 minutes and 30 seconds. Uber in the real world, their goal is to keep the wait time under 10 minutes. So you can see our simulation is, about approximately what we would expect. We don't expect to hit numbers exactly, right? But it's good to be within an order of magnitude of what we might expect, right? The average wait time for taxis, meanwhile, was almost 2 hours, right? So that's just a huge difference. And it's even more apparent in the longest wait time. The longest wait time for Uber was about 1 hour and 40 minutes. It was actually less than the average wait time for taxis. The longest wait time for taxis was almost 8 hours, right? So someone who got on, that means that someone right in here around 6 p.m., so this was even before the big surge, someone right here got on and tried to get a taxi and didn't get a taxi until close to midnight, right? That's just obviously, that person would just call a friend for a ride or just walk home at that point, okay? So it's not surprising that the wait times for Uber are that much better, right? That's sort of what we would expect. But what's interesting is how little people pay on average for that huge decrease in wait time. The average price per minute for Uber is 26 cents a minute. The average price for taxis is 25 cents per minute, right? So for this huge difference in wait time, we're only going to pay an average of 1 cent more per minute. Now, of course, that's an average price per minute. So the person who's paying right here during the peak of the surge, right, is paying about 5.5 times more than the person who's paying for the same ride back here in the period of low demand. So we might ask if that's fair, right? I mean, it's the same ride. Maybe it should cost the same thing, right? But another way to look at it is to say, well, at this point here, where everybody wants a ride, that ride's more valuable than it is back here because so many people want a ride, right? So really, the taxi driver over here who's paying 25 cents per minute, the same as the guy who's paying for 25 cents per minute for a ride here, is really actually the one who's getting screwed, right? Because he's subsidizing the taxi rider in periods of low demand is subsidizing the taxi riders in periods of high demand, right? And then the other thing to notice here is that suppose they can't do this in our simulation, but in the real world they can. A rider can come onto Uber and look at the surge price right here and say, oh, geez, 5x surge? No way. That's way too expensive for me. I'm going to wait. And he can go to a bar and wait out the surge, and he can wait for a full hour or even 2 hours until the price comes down, right? still pay less than a guy who's going to pay for the taxis, because down here it's a 1x surge. So he's only going to pay 10 cents per minute and still get home faster, even though he's waiting for 2 hours at a bar, still get home faster than his friend who's in the taxi world, right? Because the guy in the taxi world is going to have to wait potentially, 8 more hours to get a ride home, right? So the friend here in the Uber world, he can go spend his extra money on beer and still get home faster than the taxi world, right? Another thing to note, the driver's salary, big important part. We want these Uber drivers, they're on the road, they deserve to make money, right? Same as the taxi drivers. The Uber drivers, for just 26 cents, just 1 cent more per minute than the taxi world, the Uber driver makes almost 50 cents more per minute, per hour, right? So just 1 cent more per minute for the rider equals 50 cents more per minute, per hour, for the driver, right? That's a pretty significant pay increase if you're doing this over the long term, right? And it's at the very least as fair to the Uber driver as it is to the taxi driver. Another thing to note is just if we're concerned with social good, right, then we want to be able to provide more rides to more people, right? Uber provides 711 rides to the taxis 197. So it absolutely crushes taxis on this, right? So this is great. This is a nice simulation. It seems like we've pretty well proved that, at least, under the circumstances, the settings we had here, that Uber can really outperform taxis when its only advantage is its surge pricing and its flexible supply of drivers, right? But we want to ask how those results compare to the real world, right? So in the real world, we just want to make sure we're not expecting that this is going to match the real world perfectly, but the trends should be similar, right? So the trends should be about the same. So this is some real world data from Uber. Uber publishes all their data. It's available. You can go run whatever statistics you want on it. And this is from a Chicago School of Economics professor did this study. Full disclosure, Uber asked them to do this study, but it was published and peer reviewed, so it's not like it was dripped off, right? It's not made up, right? This is based on real Uber data, right? So let's compare this surge period in the real data to our big surge right here, right? So this is what our surge looked like, right? And this is a real world surge here. So we can see they have, in this simulation, unlike us, they have two measures for measuring demand. They have the number of users who are opening the app, right? So in the real world, users can open the app and say, oh, that's too expensive, and they can close the app, right? In our simulation, they can't do that, but for them, it's a good measure of demand, right? The other measure of demand is the actual ride requests. That's the same as us, as the blue Uber requests here, right? So they're measuring, they can see here during the period of surge from about 10:30 until about 11:45, the number of ride requests went up. Here's the trend line, went up over normal, right? And presumably the surge, well, we know the surge went up during this period of high demand. And then the supply of drivers, which is the green, went up as well, right? So it seems like this real world data, the trends at least match pretty well with our simulation results. So that seems to indicate that our simulation is at least tracking the truth, right? There's some real world results to be had out there, and our simulation seems to at least track them reasonably well. So we can say that our flexible supply, Uber's flexible supply of drivers and dynamic pricing is at least part of their real advantage over taxis, right? And, you know, one of the things that's really, really interesting about Uber and how they use this flexible supply of drivers and their surge pricing algorithm is that Uber uses technology to solve a classic supply and demand problem. So, you know, the supply and demand problem is you have some users, you have some passengers who need a ride, and you have this big supply of cars that aren't being used out there. Uber connects the two using technology. They also use all the data that they collect, like back here. They use all the data that they collect to constantly improve their surge pricing algorithm and also to offer new services like Uber Pool, which we don't talk about here, but that's a very, very interesting use of technology. So one of the sort of key points I think of this is that many young software companies focus on creating a technology first and then a business model second. So the classic example is Facebook, right? Facebook came up with a nice piece of technology. It's a, you know, it's a really, really nice bit of work that they did on the coding. And then they sort of tacked a business model onto it, right? Advertising is usually the go-to tack on business model. Now, since then, they've done a great job making money off of their advertising. They're a great company, but still they started with just sort of, let's come up with a great piece of technology, and then later we'll figure out how to build a business model around it. Google also did the same thing. They had a nice piece of technology in their search algorithm, and they pretty much just tacked on advertising to it. Again, they do tech advertising very, very well. They're the most profitable company in the world. But still, they're this technology first, business model second kind of company. Uber's really very different because they're a business model first, this classic supply and demand problem, and a technology second company. So they found this problem and they use technology to solve it, right? The last thing I want to leave you with is that you can test, because those inputs are flexible, you can test different scenarios. So a couple that I test in my paper is I test a constant low demand scenario, and I also test an emergency scenario. So there was a big one when Hurricane Sandy, I think it was, came through New York. The Uber surge price went up, right? And a lot of people were very frustrated by that. This simulation here, you can test some of the different results and some of the consequences of having a surge pricing algorithm during an emergency situation like that, right? So you can see how I modeled the emergency situation is I basically made it so that people would need much, much more incentives than normal to get on the road. And here's some of my results, and I talk about those in the paper. There's a few others. You can go to the simulation and try for yourself. You could try an emergency with a max surge. We didn't really talk about the max surge, but you can set one in the simulation. A lot of cities have thought it was a good idea to put in a max surge into Uber to require just, you know, a maximum 2x surge or something. You can try the default with some more taxis and see how that affects the results. And another idea is you might change it with rapidly changing demand. So you might spike the demand up and down very quickly and see how Uber and taxis deal with that. Okay. So, any questions?
I have a question. What's the algorithm that, like the cellular automation?
Say that, Dan. Could you? It was a little hard to hear.
Sorry. Actually, I want to add on to this. First, if you would repeat the 3 different forms of code that you used. And then also, your question was, what was a cellular What?
Automation.
Automation.
They're like the cellular automation.
Did you hear that?
Okay. So it was all written in JavaScript. jQuery is like a JavaScript add-on, so that was still JavaScript. And then just the front end is done in HTML like most websites, right? So the little images that you see running around, that's all in HTML. And then you had a question about the cells?
Cellular automation. This is the
Cellular automation is what it's asking.
this is the algorithm we use in China. I have simulated something like this. Use the algorithm. The same, and I think we are the same. Use the same thing. Maybe that's I think. I ask this question for you. Maybe use the cellular automation.
Apparently, it's an approach he uses in China. He's written some code that does something similar. I mean, not for this problem, but for something else.
Yeah, for the problem.
Okay.
Okay. So your question, I'm not super clear on what the question is, but you have some similar code that does some automation, right?
Yeah.
Yeah. So we kind of went over what the algorithm does at a high level. The code is open source, so you can go look at the actual code level. It's pretty clean code, so it's pretty readable. But basically, it's the way the code works is there's a little counter in JavaScript that just times every, I think, hundredth of a second or every tenth of a second, right? It snaps and it does another time step, right? So there's just a little counter, a little clock in the code that every tenth of a second it recalculates all the car's positions and recalculates the surge price and the number of ride requests out there. So all the things that we went over, they're calculated every tenth of a second, I think. So, and it was all built from scratch in JavaScript. So there's no there's no what's the thing that you guys use in simulation of physical processes?
Numerical recipes.
Say that again.
Numerical recipes.
Yeah. There's no back-end numerical recipes. This is all just hard-coded in JavaScript.
Hey,
You had a question back there? Behind you to the right, Dan?
Yeah.
You're right.
So I guess, first of all, great job doing the simulation. One thing that I'm just, I guess, is a concern or maybe a parameter that you didn't account for is, or when an Uber driver sees the increase in price, there would probably be a lag between the time that he sees the increase in price when the increase in price happens and the time that he actually gets out on the road. Is that something that simulation accounts for, or is it do the Uber drivers automatically increase when the price increases?
Yeah, so it's a good point, right? In the real world, so another one of our simplifying assumptions, like I said, there were many more than the 4 we went over, but another one that we made is just that people get on the road at least very, very quickly, right? So, in the real world, it takes drivers a little while to get out and on the road. But another way to think about the supply of drivers problem is that really what the surge algorithm is doing is it's not so much just hugely incentivizing people on the road, which it is doing in a more subtle way, but it really encourages drivers to go to the surge area, right? So the surge areas are pretty small. They're a handful of city blocks in a lot of cases, right? And this model really kind of models that pretty well, because in that case, the drivers are already out on the road and they drive pretty quickly based on what I've seen from the Uber data to the area of surge. So another way to imagine this simulation is it's not like guys are getting out of bed and jumping in their car down the fire pole into the Batmobile and getting on the road real quickly, right? It's more like they're already on the road and they're in an area of the city where demand is low, and then they see on their phone that there's a really big surge in downtown near this concert, and they all drive to that little, that handful of city blocks, right? But yeah, it's absolutely true. I mean, there's, Uber drivers would not respond this quickly to a surge price, right? And that would be an example of something that, maybe someone could go take this code and build in a delay there and see how that affects the results, right? Maybe that really eliminates any advantage that Uber has. They don't leave in this simulation just as soon as the surge price drops. They actually stay on the road until they go for about 20 minutes without picking up a passenger. So I did make an assumption on the other end that an Uber driver who's already on the road isn't just gonna leave as soon as the surge price drops below, right? He's gonna stay on the road and pick up passengers until he doesn't pick up anybody for a little bit.
Richard?
Sorry, one of the students wanted to ask, have you played with scaling the city size at all? And does the amount of successful rides scale linearly with city size, or is there any kind of delay in response?
That's a good question. I haven't played with scaling up the city size. I did create the grid automatically, so it would be really easy to do. So that might be worth doing to see how that affects the outcome. If I were going to guess, I would guess it would definitely cause a delay in the in the ride response, absolutely. But my guess is it would affect both the taxi world and the Uber world equally. And so for a comparison between what's more effective, the surge pricing and the fixed pricing, my guess is it would not make much of a difference. If it did make a difference, I would guess that Uber's advantage would be even bigger, right? Because there would just be, it would take even longer for the small amount of taxis to end up in the same spot as the passengers. But yep. Mm-hmm.
Any other questions? How did you get the price, the amount of money that the Uber and the taxis were getting? Where did that come from?
You mean the defaults?
Oh, is that a default?
Yeah, that's just the default. They're adjustable, right? You can adjust them in the simulation. What the price per minute, the default, the baseline Uber price and the taxi price is. That's adjustable, right? So I fiddled with it, I created the simulation and I tweaked some of those things to just get them to be human readable values, to be honest, right? This simulation is absolutely built for a popular audience, right? So I just tried to get it sort of like in the range of things that people are kind of generally used to paying for an Uber. I didn't try to hit exactly averages around Uber. I just didn't want it to look like Ubers were costing $1,000 and taxis were costing, $900, because people would just, it just wouldn't make sense to people. So.
And, Kevin, does Uber ever go lower than a certain value?
It never goes lower than the 1x, right? So actually they set, and you can see that in the simulation, the baseline Uber price is much, much lower than the fixed taxi price, because they only ever go up. So I think the average Uber surge is like 1.2, 1.3. And if Uber drivers were only ever making the baseline, the 1x surge price, they would probably not be making very much money. So no, they never, that's sort of a complaint, and it's ultimately, of course, it's a psychology thing. People like to feel like they're getting things on sale. So, what clothing companies do is they set the baseline price high and they sell things on sale. Uber can't really get away with that because drivers don't want to get on the road if they think that they're getting half the normal price. So Uber sets the baseline price low and increases it.
Hey, Kevin, thank you so much for showing us this stuff. Very, very interesting.
Thank you.
All right. Thank you.
Yeah, so just go to the site if you're interested and mess around with it, and feel free to email me or Dan if you have any questions. Thank you. Bye.
Hey, I'll be in touch. Take care. Thank you.